Okay, so next question to do is question 77. What's the hybridization of the indicated atom in each of the following molecules? In general, I think students take this kind of question way too seriously. People try to make it very difficult, but in reality, hybridization is actually, figuring out the hybridization for an atom is actually very, very simple. So don't get distracted by other connectivity. There are really only a couple of features that you look for, at least for the atoms that we're interested in. So again, hydrogen, carbon, boron, nitrogen, oxygen. Um, Very, very simple guidelines for how to figure out hybridization. But just because it's simple doesn't mean that they're not important. They're actually very important because these very simple rules allow you to have insight into three-dimensional geometry, and from that you can actually get a lot of good insight into reactivity later on. So don't take this skill for granted. It's actually very, very useful, and it's also very simple. So being able to have a very simply executed skill that's actually really useful is actually very difficult to come by, so don't take it for granted. Anyway, okay, for sub question A, the arrow is pointing to this carbon right here. So the main thing we're going to look at is going to end up being this double bond right here. Okay, so this particular carbon, if we were to draw it out, we would have a carbon and then the second carbon, and then we're going to have a double bond. Okay, so if we're going to draw this molecule out very simply in a Kekulé type structure, it took me not even a full 2 to 3 seconds, versus drawing it out as above would take a bit of time. Okay, and they're the exact same molecule. So this molecule right here is the exact same thing as this. Okay, so if now instead of looking at this carbon right here, we're looking at this guy. So the main feature is this double bond. So if you see a carbon with a double bond, it's going to be sp2. So we only really have 3 possibilities, so you have pretty good chances of just guessing, even if you don't remember these guidelines. But overall, this guy is going to be an sp2 hybridized carbon simply because it has this double bond right here. Okay. Question B. If we're going to draw this molecule out very quickly, very simply, without having to draw all the carbons and hydrogens, again, we're drawing the Kekulé type structure. This is what it would look like. So carbon 1, 2, and your oxygen, and then your third carbon, and done. So again, this is carbon A, carbon B, carbon C, carbon A, B, C. And again, all of the hydrogens on carbon C and carbon A are completely implicit. They're not necessary to draw out. Nor is it necessary to draw out carbons A, B, or C. Okay? So those are all completely implicit as well. Okay? So thinking about this, kind of going off on a little bit of a tangent, it's good to be able to go from this bit right here to the Kekulé structure, but it's also, again, very, very important. If I didn't give you this top structure right here, it is extremely important for you to be able to look at this carbon C right here and to be able to very instantly recognize that carbon C has 3 additional bonds that are there to hydrogen, but they're just not being drawn. Okay, and so this comes into play whenever we're going to end up drawing more complicated reactions, and being able to make sure that you're absolutely sure of the overall charge on a molecule. Okay, so again, an extremely important skill to have, to be able to go this way, down to the Kekulé structure, but also being able to, in your head, be able to go back up to this, more, explicitly drawn structure up top. Okay, all right, tangent over. Next part, so question C, or sub-question C, we've got 2 carbons and an oxygen, so let's just draw this guy out very quickly in the Kekulé, so 1 carbon, 2 carbon, then oxygen, and hydrogen. This is an exception to the rule, by the way. So another little mini tangent. The whole implicit hydrogen thing only applies to carbon. So if you have an oxygen, this is an exception to the rule. Whenever you have an oxygen, you always, always, always want to draw out this hydrogen right here. It's extremely important to draw it out. Otherwise, if any chemist looks at this and you didn't have that hydrogen right here, if you had it like this, that chemist would assume that you were saying well, that oxygen has 1, 2, 3, 4, 5, 6 lone pairs. That's what they would assume. And because of that, that would mean that this oxygen would be negative. Obviously, that's not the case because of the way we've drawn it up here, but again, if this top structure wasn't here and you did not draw this hydrogen up here, this is what people would assume you were saying. Okay, so again, I know at the beginning it's a little frustrating because there are these little exceptions, but really, again, we're only dealing with a handful of molecules, and so there are only really a handful of rules to remember. And this is a very subtle rule, but it's also an extremely important rule for any atom that's not a carbon. So basically, nitrogen, oxygen, anything else. If you want a hydrogen to be there, you need to show it. Okay. So this is the molecule overall. Again, this is very quickly drawn. If I wasn't babbling on, but oh, whoops, sorry. So going back to the problem B. The hybridization, right? So the hybridization of this oxygen, basically, again, all we're looking at is what kind of bonds we have to oxygen. So this oxygen has a double bond here, so it's going to be sp2. Very simple. Okay. Next up, carbon C. This is the oxygen we were interested in. We've got 2 lone pairs right here. So we only have single bonds. So because of that, this oxygen is going to be sp3 hybridized. Next up on the docket, if you want to draw this guy out, completely rigorously, you could, or very quickly, this is what it would look like if you didn't want to include the carbon or the hydrogen. So this guy is interested in the nitrogen, so the nitrogen has 3 bonds to it. So this is the last permutation on our 3 possibilities. So if it has a single bond, we're going to have sp3, double bond sp2, triple bond sp. So this nitrogen right here is going to be sp hybridized. Okay, and again, thinking about the way that this molecule is drawn, it's given to you with the intention that this molecule is neutral. So one thing, you don't always have to draw out the lone pairs for heteroatoms, which means a heteroatom would be nitrogen, oxygen. But if you wanted to include them, it's not a huge deal. It's good to be more clear than less clear, basically. So if you didn't draw them out, I would assume that they were there. But it's good to always draw them out just to make sure that your intention is known. So again, just to make sure that this nitrogen is neutral, let's do the formal charge calculation. So nitrogen has 5 valence, so it's going to be 5 minus 1, 2, 3. So minus 3 minus 2 is going to be equal to 0. So nitrogen has a charge of 0, which makes total sense. Okay, so again, let's redraw E first. So 2 carbons attached to a nitrogen. So we're going to have 1, 2, then a nitrogen. Okay, so let's draw that double bond to the nitrogen, which is implied right there. So we have a carbon double bound to a nitrogen, and this nitrogen is going to be bound to another carbon right over here. So let's go ahead and do that. Okay, so again, everything is assumed to be neutral because the molecule doesn't have an overall charge on it the way that it's been presented to you in text. So to me, that means, okay, how can we make this nitrogen neutral? That means 5 minus 1, 2, 3, so that would be 5 minus 3. Right now, if we did nothing else to this nitrogen, it would have a +2 charge. Easiest way to get away from that, give it a lone pair. Okay, so that's minus 2, that equals 0, nitrogen is neutral. Okay, so we've added our nitrogen, we've got 1, 2, 3 carbons, 1, 2, 3 carbons, okay? And again, the question is what's the hybridization on nitrogen? Nitrogen is double bound to something else. In this case, it's a carbon. And so for that reason, this is going to be sp2 hybridized. Okay, so finally, question F. So let's redraw this guy and calculate. Very quick structure, so carbon 1, bound to an oxygen, bound to another carbon, bound to another carbon. So now the question is in regards to this oxygen, what's its hybridization? And again, it's neutral. The easiest way to make it neutral is to add the 2 lone pair of electrons. And so after we've done that, it's obvious that this oxygen only has 2 single bonds attached to it. So just like up here with question C, in this case, this oxygen is going to be sp3 hybridized. So sp3, sp2, 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 sp3, and sp2. Okay, and it really is just that simple. Okay, so don't get caught up with worrying about hybridization too terribly much. 99.9% of the time, it's as easy as that. Okay, next question.